Recording. All right. Hi, everyone. I'm Paul, and I'm going to talk about what I've been working on, which I've been really excited about, but I don't know. We'll see. It's kind of cool. Get rid of this. Okay, so I'm going to go over to the screen recording and go in the presentation. Where is that? Present. Okay, so I've been looking at neural networks and just trained networks. So not really dealing with network training, but with looking at once they're already trained, what sort of properties do they have? They obviously take in some input and produce some output, as we know. You've seen they can take in an image of a dog and then pull out hierarchical features, figure out some very early things well, there's edges and shapes, and then those compose into larger structures like a whole face of a dog or a whole body of a dog, and then those relate to each other. So we know that that works, and I want to know how, in what ways, and what sort of computations are these networks doing that actually implement pulling out those features. We're not really concerned with how they're trained. We're just going to assume backpropagation kind of does that automatically. We set up a network, we feed data into it, that data gets represented in the network somehow. But once it's in there, how do the computations actually work? There's been a lot of talk over the past 10 years about neural networks being kind of like software 2.0, that you're, instead of writing a program, you couldn't really sit down and write by hand, here's how I'm going to code a program that'll look at an image of a dog, be able to tell it's a dog. It takes a lot of code, it takes a lot of hand-designed algorithms. Neural networks are the thing you would use for that, because they're going to learn that program automatically. They're learning the software. But what actually is that software? What would the program be? We don't really know. And if you look at the weight files of a trained neural network, there's megabytes or gigabytes of weights. That's a lot of source code if you're considering that's the code of the program. And I'm under the impression, and from what we're looking at here and what other people have been looking at as well, that the actual computations that are happening are a little bit more compressed than that. There's not actually megabytes or gigabytes of code involved in these computations. There's a bit more organization to it. So that's the goal of why I started looking at this. And now I guess we'll get into it. So the main idea is that we're talking about neural network layers as vector fields that have an input space, and they define some transformation on that input space. So at any point you're at, if you're in 2 dimensions, you're on an XY plane, there's a transformation that you're going to take from any point to some other location in that same plane. You could draw an arrow from the input to the output, and you could do that for any point. That's a vector field. So some background information, related topics are iterated functions. If you have a function, which a neural network layer could be considered a function, it's a function approximator, then that function, if you iterate, if you take the input, get an output, feed that back into the input again, you can just continue doing that. You'll get sort of a trajectory. If you start at a point, it'll move to another point, another point. That's what's happening here on the left with this ordinary differential equation that defines the Lorentz attractor, which is a 3-dimensional system. It's got 3 equations. And you can start at any point in 3D and follow a trajectory that that point takes. And even though there's simple equations that define here's where the point starts and here's where it's going to go, you get some really interesting patterns out of that. It's chaotic. There's sort of these 2 butterfly wings. That's been talked about a lot. That's the Lorentz attractor. Another iterated function is this function that defines the Mandelbrot set. You take any complex number, C, and then you start iterating this equation, starting at z equals 0 and going up from there. And the way that this image is produced is if the pattern diverges and just goes to infinity, it's one color. If it doesn't diverge, it's another color. And you get this really complicated looking set of numbers just from this one equation. So neural networks are also just a function. They have some linear terms and then some nonlinear functions that compose them. And we can do the same thing with that function. And that can tell us something about what the network layer is actually doing. So normally in a neural network, we do like a forward pass to compute some output, and then during training, we do a backward pass looking at the derivative of the function. Well, we could also just keep doing forward passes over and over again. So that's what I've been looking at, or part of what I've been looking at. I guess I'm going to show this. So some other related work is with power iteration. This is a technique to get the largest eigenvector of a matrix, which kind of just means like finds like what this matrix's attractor is. So matrices, functions can have attractors. Those are like the attracted state of that function, kind of. And it turns out if you take any random point, any random vector, which defines a point, and you multiply the vector by the matrix, and then you take the output, multiply it again, over and over again, you'll converge to this same point. And that point is defined by another vector. That vector is the largest eigenvector of the matrix. So this is a technique that people use to calculate the eigenvector of a matrix really quickly. They take any random vector, they multiply it by the matrix, they normalize that output, which will come in later, and then they feed that back through the input again and keep multiplying, and they'll get to this eigenvector, which is like attractor. Like once something goes to that point, it's not leaving there. If you keep multiplying over and over again, you're not going to leave that point. You're going to stay at that point, and everything is just going to collapse to that point. So it's like an attractor. Like that's what it means.
So the largest eigenvector is basically the attractor of the network layer weight matrix.
Yeah, so that's at least an analogy. I don't know if that's like technically always true, but like, yeah, like an eigenvector is like an attractor, basically, kind of.
Is it literally a fixed point, or is it an attractor?
Well, yeah, so this is a fixed point.
Okay.
And when we're looking at some of these other attractors that we're going to look at, they're not fixed points. There's a lot more going on, and they're not always stable. The points won't always just converge to one place and stay at that place. They might continue moving along a path. It might be cyclical. It might be really unpredictable and chaotic. We would still just call it like an attractor. And there's some techniques we can use to actually figure out what properties that attractor has, even if we can't stop at a single point. So I'll get to that. Okay, so what I've been looking at, what brought me to this was working on transformer neural networks, which are kind of network introduced in 2017. They work like a regular neural network. They just have fully connected layers, but they have this other kind of layer, self-attention, which people think it does a lot of things. I think the most important thing to know about it is that instead of having one input to a network, you've got like your vector, which could be just a bunch of pixels in an image flattened out into one list. You multiply that by the network, you get some output. The way that the transformer works is the inputs are actually broken up into multiple vectors. So if you've got an image, you break the image up into patches. Each patch gets a vector. Or if you've got like a sequence of text, each word gets broken up into a vector. Recurrent networks work like that too. That's why transformers were created, is people were trying to make recurrent networks more efficient and able to learn like longer range dependencies. So they came up with this kind of network where there's two kinds of layers, a self-attention and a fully connected. And the self-attention operates on the words, like passing information between the words. So you've got like one vector per word, and it like compares the vectors, how similar they are, and it comes up with new vectors for each word. And then these fully connected layers that only operate on each vector independently. They don't look at comparisons between the two. They're just saying, well, this word has this location right now. I'm going to transform it this way. I'm going to apply the same transformation to a different vector that might like be in a different position. It'll get transformed a different way. So there's these two different kinds of layers, which is pretty important. It has a big effect on what the network does. Okay, so what I've been doing, iterating neural network layers, just taking like any subset of a network, the entire network, one layer. Mostly what I've been doing is taking these two-layer fully connected networks, which are universal function approximators. They're in the transformer. They're like that second kind of layer. They just operate on one word or one image patch. And I've been taking a starting point, It doesn't have to actually match up with a word or an image patch. I can just pick a random point in the input space and then multiply that in, do a forward pass, take the output, and just like in this diagram, add and normalize. So like normalize the output, do a residual connection, add it back into the input, and then feed that back in over and over again. And so what happens, if I start from up in the top right here, this is a uniform grid, just like evenly spaced out. This is in 2D. It's just on two axes in the really high dimensional space of the input. The input might have like 512 dimensions. We're just picking two axes. I'm picking these, their principal component axes or the weight matrix, which is like just a trick to get like a nice view of the input space. It's not really important which axes you pick, but you're only going to be seeing a 2D slice of wherever these points go. So I'm sampling these points, they're on a grid. We do one iteration and they get transformed. If I project them back down to those same two axes, we'll see where they go. And they're just color-coded by where they started. So we can see, like, here's what the transform looked like. But if I keep iterating over and over again, those points will eventually end up at a place where they're not going to leave the place they've transformed to. That's going to be like the attractor of this sub-network. If it's this two-layer network, that's the attractor for that. So in this example, we started with a grid. This is a network that I trained on face key points, so points that are like on like the eyes, nose, mouth, and jaw around the face. And it was trained to predict the distance between those key points to kind of like learn a representation of the face. I'll cover that a bit at the end. But what happens here, I don't know if it's totally visible, there's this sort of like triangle looking thing, and then there's 2 points. All of the points on this grid ended up on that triangle or at those 2 points. So those are 2 fixed points in a limit cycle, actually, is what's happening there. There's like these 2 points where everything that went there is not going to leave there. I keep feeding that input into the network, normalizing, doing the residual connection over and over again, and the output is not moving. It's staying at those points. Nothing's forcing that to happen. That's just what the function is outputting. Like those are like attractors that the function of the network layer is defined. And then points that end up on that limit cycle there, they might move around that cycle, but they're not going to leave that cycle. And that's just because like that's a property this function has. It has that cycle, and points that go there are not going to leave there. So we have some like interesting attractors. This is like sort of a simple example, very like proof of concept. This was a really simple network, like it's a full-size transformer. But to explain this in better detail, we're going to start with just like small toy examples, random networks.
Well, did you mention, this was a pre-trained, right?
Yeah, so this network that I'm showing here, this is like totally just like conceptual, but this happened to be trained on face key points, and it was predicting the distance between those.
Can I have a quick question?
Yeah.
So in general, what happens like the input space is converted to an output space, the dimension changes, right?
Right. Oh, I forgot to mention that. Yeah. So
Feedback, how do you do that?
this talk's kind of poorly organized. Sorry, I'm trying to throw it together quickly. But yeah, so what happens there, these networks happen to have that property, where their input space might have 512 dimensions of an embedding. The output space also has that same 512 dimensions. So you'll have like a 2-layer feed-forward network.
Oh, okay.
You have 512 inputs. There's like 2,000 or so hidden activations, and then another feed-forward layer that goes back to 512. That is like totally coincidental. Like that happens to be a property of these networks, and it's nice because we can do this analysis. Like we can take the input, go to the output, and without any sort of transformation, just feed back into the input again. Now, what we're doing here, we have reason to believe, and other people have shown, like this stuff kind of applies even if you don't have that property. You can look at convolution networks where the output is not the same shape as the input, and the function's still doing the same thing.
But how would you feedback that?
Yeah, I don't know. So I'm not dealing with that.
Okay.
But yeah, like that, I would think is totally solvable. Like, there's definitely a way to like pull out, well, here's like if you keep iterating.
And tell with the other
Yeah, that may work for vision or text, I don't know. But yeah, I haven't been dealing with that. I've just been looking at networks that have the same size output as input, which, like, they're doing the same thing, right? If you make a convolution network that has the same size output as input, you train it, it can solve vision tasks. If you have one that doesn't have that property and it like throws away some of the edges of the image each time it operates and it grows larger receptive fields, it'll still do the same thing. It'll solve vision tasks. So whatever like computations these things are learning doesn't really depend on is the output the same size as the input. It just happens that we can like analyze things neatly when they do. And recently, like transformer networks that are kind of like used all over the place in deep learning now have that property. So that's convenient.
In the most general sense, what you could always do is you just imagine literally a cyclical network where whatever size your output dimension and whatever dimensionality it is, you just then feed it back to the input with connections, fully connected back to the input.
You have to learn those.
Yeah.
You can make.
No, you don't have to learn them. I'm saying you could do this after the fact.
Yeah, well, and so there's lots of other
What are those?
I see.
work in computational neuroscience and machine learning in general that I'm not going to touch on here, but like hot field networks are kind of like set up to do that, right? Like you've got a network, it's a neural network,
That's a different thing.
but it's a totally different structure than like the idea of a like feed forward network. It's not really meant to feed forward. You're supposed to iterate. Transformers are kind of like hot field networks, but like that's a whole separate topic. This should apply to any kind of network. Like, it doesn't really matter that we're looking at transformers here. I'm not even looking at self-attention layers, which is on the list. We're getting there. This is for any feed-forward neural network. These are fully connected layers. That's all we're going to be looking at. Yeah, Matt? Oh, do you have a question? Okay, never mind.
You just add it if the outputs and inputs aren't the same?
Yeah, you could do lots of things. I mean, the point is you could.
Yeah,
they'll all
right.
be doing
Still
something.
abstract.
They'll all be doing something. It's not
So
literally the
if
output.
you're in like abstract, just like embedding space, you've got some vector, which is like a hidden representation that's not really like matching up to an image, right? So if you pad on the side of a vector with extra dimensions, like what do those dimensions mean? They're not necessarily pixels. That might not match up with like just padding.
I think the point is here is that, you know, it's kind of arbitrary that you have, it's not really about this output layer per se. And the fact that it has the same dimensionality is just a choice.
Yeah,
Getting
so
to this gray zone of the fact that the way you pre-train, is that essential or not? Because that's what really matters in terms of this network's properties, is the dimensionality that it's going to have to do with how you end up training it.
right.
And in the end, that's sort of the only consideration in terms of dimensionality.
Yeah, so
I wanted to generalize.
I'm going to go ahead and say that like it's totally coincidence. Like there's no, you do not need to have a same size output as input. I think that it's a nice property to have. There's lots of details about the transformer that like are nice properties that I think like aren't, like they probably do help in a way that we don't totally understand. People have theories about, but like that does not matter. You can train a network that does not have that property and it will do the same exact thing a network that does have that property will do. So that part is just like convenient for us and we'll keep going with it. So here's the different ways that I'm gonna be visualizing stuff. I'll like normally be taking like a grid of points and feeding that through and iterating and showing what happens to that grid of points. We can show that in a couple different ways. So on the bottom right here, we've got some scatter plots. Those are just the same points plotted on 2D. They're like plotted on some low dimensional representation of wherever they are in embedding space. It could just be like two principal component axes. And those points are colored by like where they started on that grid. So if they like started on the right, they'd be yellow. If they started on the left, they'd be blue. We can see how those differentiate. Or they may be colored by time step. So in this case, they're colored by where, like, is this a later iteration step or an earlier iteration step? And so we can see those points sort of like start and move towards this limit cycle. And depending on what low dimensional representation we're looking at, if we're looking at two axes or two different axes, we'll see like a different projection of the same thing. These are the same points in the same embedding space, but if we pick two axes, we'll get the left image. If we pick two different axes, we'll get the right image. So we can see a different shape, because things are high dimensional. We're only looking at a small slice of that high dimensional shape. It might be like convex versus concave, depending on how we pick the projection. But we still see that same cycle, and the points will still move around it the same way. this structure has the same properties. Like whatever we calculate about it, it's the same limit cycle there where points move to it, they're attracted to it, they move around it. They're not leaving that. So we'll be seeing different views of the same thing. It's kind of arbitrary how we're looking at it. Doing stats on it is definitely like the proper way to analyze these things, like actually calculating properties about them. So that's what I'm working on like at this minute, and we have that later in the presentation. Another way to visualize this stuff is to take a grid of points and just show an image, which is up on the top right there, where the image is that original grid, each point is a pixel, but it's colored by where those points ended up as the iteration goes on. So it might be colored by like the 2-norm distance from the origin, so just like vector from the origin to that point, how long is that vector, what's the magnitude, that's what it would be colored by. It could be colored by the L1 norm, whatever. So like in this grid of images here, we're moving to the right and then down through iteration steps. So we'll start with points that are maybe like random normally distributed or uniform distributed. They're a certain distance from the origin. And then we see those colors change. Points are transforming nonlinearly. So bright yellow points would be farther away. Blue points would be closer. And there's like interesting patterns that form there. We'll see a couple of different things. Sometimes we'll see like things collapse to a single point, like a fixed point, like we were seeing earlier. Sometimes we'll see like cyclical attractors, like the limit cycles there. And then sometimes things are like very chaotic. They're moving all over the place. There's a big diversity in the kinds of attractors that we'll see in these networks, whether they're random or pre-trained. So that's really where the interesting stuff comes in about what that says about these functions and what properties they have. And then the third way to look at these is to just kind of plot out a line graph of all the time steps on the x-axis and where some property of the points goes on the y-axis. So if we plot like distance from the origin on the y-axis and time steps, we can see points start off and move through like as they transform. And then we'll sort of see like a diagram of like what the attractor looks like. We'll see like here's a fixed point on the bottom that sort of disappears and becomes unstable as this iteration goes on. And then here's these two other fixed points that are stable and points are attracted to them. They happen to be alternating between them here because this is like a discrete approximation of a continuous system. But what we'll see throughout all of this is that these neural networks are function approximators. Like they're learning a discrete approximation of a continuous function. So these functions are like definitely continuous. And you could plot, even though we're seeing like single discrete time steps, a function that moves through them and it would have like continuous properties that would form a curve. And the network's doing a good job of approximating that. Like it is fitting a continuous function, and these like could be modeled by differential equations. No clue how to get those equations. The networks are learning them from the data though. So that's like how we're going to be visualizing stuff. And what do we have next? I was also doing some like phase plots of just showing like one time step on one axis and then the next time step on the other axis. So you can see like if a point is at one place, where's it going to go next? And those look interesting when we have high dimensional space. So these are kind of hard to see from far away. It might show up better on the recording. But you can see some really interesting structure that's indicative of what the attractor for these networks looks like. Like there's points where most of the space will end up, and then there's like longer cycles where a few points will go. And those are like interesting regions of input space that are actually doing cool things on the data.
Wait, I have a question.
Yeah.
What do you mean random networks showing?
Oh, yeah, so we're going to get to that in a minute, but these are random neural networks. They're not trained on anything. Yeah, so if you
But they
pick,
have structure.
yeah, so if you pick a random initialization, not only will you get cool things like this, you'll get a diversity of different attractors, and most of them don't look like this. So I'm going to skip that for a second. Most of them look like this here on the left. It might be hard to see. There's two fixed points there. They're like kind of faint yellow. So we started with a grid here, and we watched the points attract. This is a scatter plot, and all the points end up at 2 fixed points. If you randomly initialize a network, no matter how big it is, if you have more neurons, more like dimensions of a hidden embedding, you might get more interesting structure more often. But if you have a random network, like I didn't do probabilities on it, I'm gonna do that, but you'll get like fixed points a lot of the time. And then sometimes you get like interesting structures. There's diversity in like what kind of attractor you'll get. And I don't know how that works. And I don't know if anybody else is. Like there's diversity there that will happen if you use the same initialization strategy. So people are initializing their networks and they're training them. And the thinking is, well, if you initialize a network that has like orthogonal weights or that has like normally distributed weights or some property, like you have a good initialization strategy, it'll have these properties, and you just do a random init and train. But there's also an awareness that different random inits will have different outcomes sometimes, and that's like a whole field of study. Well, we're seeing here a way to differentiate random initializations that we weren't able to before, so that's like interesting. We should look at that, right? So I guess I gotta get back to this. Yeah, but just in random networks, you can get some like really interesting looking attractors.
You could potentially evaluate them before they've even seen data and say, this is really not like a good.
Yeah, right. And I talk about that a bit later, but like there's certain ways that I think you can and certain ways that like that may not be, like it might not be relevant, like how this network starts if it's going to get trained. The way that that's relevant is not known. So like we have to figure that out. I don't know. Well, anyway, this is a couple of different ways that I'm visualizing stuff. So this is that face network again. And we can actually see the iteration play out here. So maybe this would be like a better visual. We start at a grid. We see the grid of points there, right? And then quickly we move to this like circle looking thing. That circle, if I can get to it, well, kind of, it's on the first frame. So that circle is a result of the normalization that happens in the network. These transformer networks use something called layer norm, which is kind of like normally distributing all the different embedding dimensions. So what will happen is everything will kind of get like its magnitude from the origin normalized. Everything will like move pretty close, but not exactly, to like a ball around the origin. So we end up on a circle in this projection, but then we start deviating from that circle because we're not actually just going exactly to that magnitude of the ball. That's just the mean of all the different embedding dimensions. So some dimensions are a little bit above the ball, some are below, and that actually encodes information in a way that's meaningful and can be used later by the network to figure out where things should be oriented. So most of the computations that happen in this network are done using orientation, like where things are pointing, the distance will get normalized. But when the distance gets normalized, it'll treat things pointing different directions differently. And so they'll end up slightly above or slightly below that mean distance from the origin. And that'll encode information for the next layer that'll lead to things getting pointed in a different direction there. That's how the computation is actually being done in these networks. And we can watch that play out where points that start on a grid, get blown up to that ball, quickly lose that shape. Now they're all over the place in this projection. What's actually happening here, they're moving through high-dimensional space. So these points are in 512D. We're just seeing them in 2D. We're seeing them along two principal components. And what looks like a big mess of points here, it looks pretty cool, they're actually really far away from each other. So different points are moving different directions, all over the place in 512D space. They're all moving around. And we see like sort of like lines of points move together. That's an indication those points are in the same part of space, following the same or close to the same trajectory. They started together, they're moving together, they're going to end up at the same place together. And if 2 points are at the same location and they overlap, and some of them go one way, some of them continue the other way, then they're in different parts of space. Points that are continuing one way are all together, points are continuing the other way are all together. In the projection, they overlap, they might be really far away in the actual space. So that's what's happening here, but they all sort of end up on this loop that we see. They're all ending up in the same place in the space on the same attractor. It's this cyclical attractor, this cycle, and the points are like getting there, they're converging. Some are already on the attractor, some are like getting closer. They'll eventually all end up just looping around here, and they'll continue looping, they'll continue moving around. They're not gonna leave this attractor though. They're there, they're moving around it. So this is a trained network, it's trained on those phase points, and it's doing the same thing that we'll see in the random networks, where like this network layer or set of layers has an attractor, points go to it, and they don't leave it.
And what does this network train for? Like, is a transformer doing?
Yeah, so this is a transformer trained on phase key points. It's got those points, and it has to predict the distances between those points.
Okay.
And what's interesting here, I'll talk about it later. It's not a good network. It's not doing well on downstream tasks. And we figured out why by looking at this. So that's cool. We already kind of made use of it.
I have a question.
Yeah.
If you weren't, if you're.
Yeah, sure, go ahead.
Sorry, I wasn't sure if you were done. Okay, I have multiple questions. My first question is, can you first, you said that, in the beginning, when you were showing this, you were saying that some points are moving in different directions. Can you like maybe point to where that's happening? Because to me, it looks like they're all moving in the same direction.
Okay, so over here, look, there's some points that are,
Because if it's like on this cycle thing, then they're all like just on this like racetrack.
yeah, once they get there, yeah, they're all following that
But
cycle.
here, they're not doing that.
So here, there's some points that are like moving up, and there's some that are moving down, there's some that are moving left, some that are moving right.
So that's why we have different colors?
So the different colors are the same colors as where they started on this, it's kind of dim, but on this input grid. So points on the left side are one color, points on the right, another color.
Like the plot, like the slicey thing.
Yeah, I was not good with the colors here. So this image on the right is an image of all the points where they started. So they don't leave that place where they started, but they're colored by where they end up. That'll potentially look like a fractal if the attractor has fractal structure. You're seeing like where the points start. They're colored by where they go, so you have kind of like a map of where things end up. That's like how you would make a fractal. Like you'd take a starting point and you'd indicate how does that starting point end up after you iterate a function. So the same way that Mandelbrot set gets made, that's what we're doing here. It's just that things might not look like a fractal if they don't have fractal structure. So like this map here shows the same exact thing, same points as this scatter plot. So points that are all colored yellow here are all the same distance from the origin. That's what I'm actually showing with this color. Points that are blue are the same color from or same distance from the origin. And so if they have the same color at the same time, they're in the same place on this attractor, we could infer. And as these points that are starting in different places of space end up on the same place in the attractor, we see like which regions of input space are getting treated the same, are getting mapped to the same place. The colors don't match up.
It's really a derivation of the same distance, but because this thing has an odd shape, distance will kind of correspond to some place.
Yeah.
That's why you're saying that the same color is the same region.
Right, yeah. So like what we're seeing is points are actually like in the same location on this loop, because this loop is not like equidistant from the origin. So some points are further away, some are closer, and that's the differentiation in color on the right. And then on the bottom here is that like line plot. We can see the points start off, they blow up in magnitude, and then there's like a period of like total like chaoticness where the points are all moving around. And then there's this periodic, like they are on a loop, it's the same exact periodic function, and there's a time lag between some of the points. Like they're at different phase from each other, they're at a different place on this loop moving around it. So we know why this happened, and we know what this network is actually doing, and I'll get to that at the end. But this is like a really simple example from a network that was trained on some really simple data and learned a really simple computation.
Wait, I
We're-
had another question.
Yeah,
Can you just explain kind of the time, like, what is the time scale here? Because I know we're like, you're showing this picture go through time, so
right.
what is each like?
Each
step?
frame is an
Yeah.
iteration step.
Okay.
So things start off moving very quickly. Like we lose that circular shape really quick, and things are like moving around. And then later on, things are like, I mean, we see they're moving at kind of like a constant speed, I guess, but like,
Because you can actually see the speed because each frame is the same.
yeah, right.
That's really cool.
This is continuing to move, and it's moving like at the same speed. That doesn't happen in most other networks that we'll look at. Like most things kind of cool down. Okay, pause that, and great. So now is where we probably should have started. Simple examples, toy networks. This simple image with two fixed points that are barely even visible. We're showing the same thing, grid of points, uniform distributed, and they end up at these 2 points because the network that they're getting transformed by is really, really small, really simple. It's got 2 inputs and 2 outputs. So this isn't like a projection of anything. This is the input space. X and Y are 2 inputs, 2 outputs. And there's 8 hidden activations. So we have one matrix that does the linear transformation. It's got 2 inputs and 8 outputs. We have a second layer that has 8 inputs and 2 outputs. That is just randomly initialized. And pretty much every time that I've run that, I get 2 fixed points. Never more, never anything more complicated, just 2 points. So I tried adding more hidden activations. What if we have 2 inputs, 2 outputs, but 1,000 hidden activations?
And these are random networks?
Yeah, randomly initialized, right? We still have 2 fixed points, no matter what we do there. So there's like a little bit more of a loop here you can kind of see. That goes away as we keep iterating. All these points will end up at those fixed points. It might take a few thousand iterations, but random network always going to have 2 fixed points or less if we have 2 inputs and 2 outputs. Well, if I add a third input and output and just project that down to 2D, now we see like a fully completed loop, and that stays there. As we keep iterating, it doesn't go away. This doesn't have to happen. Sometimes if we have 3 inputs and 3 outputs, we'll get 2 fixed points. Sometimes we'll get a loop. It depends on the random initialization. So different random functions will have different attractors. Yeah?
Do you know that there's no 2 inputs, 2 outputs version that's doesn't just go to 2 points, or did you just use induction?
I don't know that. I have not proved it. No.
Okay.
I just ran this like 100 times or so and kept seeing that. And like I was scaling like, okay, well, here's 2, here's 3, here's 4, and so on. And here's like the dimensionality of their attractor, and like made kind of like a face plot of that. I don't have that in here, but that's in the works, which is kind of cool. I'm not familiar with like
We can construct.
the way to prove that,
We
but
can construct ones that will.
that will what?
2 inputs, 2 outputs, we can construct things that will have
Okay.
a cycle, but they're not likely.
Okay. Yeah, so I don't know about that. But in general, the important part here is that the number of hidden activations is obviously important, but there's sort of an upper bound on the dimensionality and the structure of your attractor based on the size of your input space, like the actual like embedding that you're projecting your data into. So if we have 100 inputs and 100 outputs, then we get some interesting high dimensional structures. Projected down to 2D, they look really cool. In the high dimensional space, they're like a mess to look at. You can't really visualize that. And then we just need enough hidden activations to like be able to learn interesting functions. But the important part here is that you have like an upper bound on the dimensionality of your attractor based on your embedding size. And so that's like that agrees with the understanding that you need like a high dimensional embedding, that having high dimensions lets you like learn interesting functions. Okay, and then if I look at networks that are like the size of a transformer we might train on some data, like 512 embedding dimensions, full-size weights, so like hundreds of megabytes of weights, and just randomly initialize those the way you would if you were going to train a network. We get interesting functions, but also like diversity of functions. There's some that will collapse to a fixed point. There's some that look like really like strange attractors that have like chaotic properties. There's some that are like cyclical. So we get this diversity. We can determine what properties the attractor has for random initialization, and they're not like we know that they're different from each other, but we don't know how. And the same exact strategy for generating these weights will give you functions that have different properties here. So it's probably important. I don't know. That's all I know about it so far. Yeah, right. So most of the time, I'm just getting like simple, like things collapse to a fixed point, but occasionally randomly generating something, you get like an interesting structure. So Elon, we had talked about, well, can this be used to like determine a better initialization? And we don't know. The only thing that would make sense here is, okay, well, if we pick a random initialization, we're at one point in weight space. Of all the possible weights we could have, you could picture like that really high dimensional space. We're at one point there. It has an attractor with certain properties. Different attractors at different points at a random initialized weight would have different properties. And you could picture there's like a threshold where if you cross a boundary in the weight space, the property of your attractor is going to change. You might move from a fixed point to a cycle. You might like have a fixed point go from being unstable to stable. Many things could happen. So this is like totally conceptual, but you could like kind of visualize, like you could color code things by their attractor. I haven't done that yet. Working on some interesting ways to do that. We'll see. The interesting thing here, I think, is that we already look at the space of all possible weights when we're doing optimization. When we're doing backprop, we have a loss function, which is a function defined for every point in the space of weights, and it has some loss value. And people study that loss function and loss surface. That's like an active field of research. This is like another surface that could be looked at. It's kind of expensive to compute this stuff, but if we can say something about what properties a random initialization might have, if statistically having a initialization that has certain properties would lead you to better training later on, that would be useful. We would like want to generate weights that have a certain property that maybe wasn't known about before. So that, I guess, has to be looked at. Haven't done that yet. But there's also no reason to assume that these two functions would be related to each other, that the surface of attractors would have anything to do with the surface of loss functions. It may, we don't know how, and if you pick a point and you start at that point, when you train, you're going to end up really far away from it, different location in weight space with totally different attractor. The place where you started might just be like random, and it might be like fractal, it might be like chaotic, and so you might be picking a point that has a certain property, you move a little bit to the left, it has a different property, you move a little bit to the left, it has a different property, and you're going to leave that space. It doesn't matter what was there, you're going to end up at a totally different place that has different properties. That could be what's going on, and in that case, it wouldn't really matter where you start.
So like the attractor is random in the beginning, and then
Yeah.
through training, the attractor is going to move.
Right.
So the attractor has an attractor.
Right. Yeah, they're sort of, right. So we're looking at like embedding space, and now we're talking about weight space, like two different things. Those are related. I'm not going to get to that. I'm not really looking at training. I kind of set that as like a limit. I'm not going to look at backprop at all. But yeah, that like could be looked at, and the diversity we're seeing in these attractors tells us, okay, well, there's something interesting about studying that surface. Like that should be looked at. I'm not going to do it, but
And if you have another thing that's determining the hyperparameters, then you have an attractor to the attractor.
Yeah.
yeah,
All the
right.
way down.
Yeah. Okay, so that was random toy networks, just to get an idea of like, okay, we need high dimensionality here. What we're actually getting with that high dimensionality is a low dimensional manifold, a low dimensional attractor that lives on a manifold. It might just be a point. In actual trained networks, it is a higher dimensional surface. it isn't the size of the embedding space. You don't have a 512D surface where all the points get attracted to. It's more than 2 or 3D, but it's like less than 12 in CLIP, which is the network that we're going to look at. So it's low dimensional is how people will describe it, but it's like more than 3D, but a lot less than embedding space, which is actually really important. So we need the high dimensionality in order to learn something that is compressed, low dimensional, that can be linearly separated by a classifier in order to like tell you, well, if a point is at this place on the attractor, it's a dog. If it's over here, it's a cat. That's how the computation is being implemented. So what I've been looking at in order to see like some interesting structures in a trained network is this network CLIP, contrastive pre-training of, or not contrast, yeah, well, they call it contrastive, but not really. So all it's doing is it's looking at paired data, images of whatever off the internet, but paired with text that was captioned on the image on the internet. So they got like 500 million or so pairs of images and text from like every website you've ever seen, every social media site. It's a really good data set, clearly, because this network is really cool. I didn't put any of the cool art in here, but like this thing can kind of like create images if you give it text. If you just give it a sentence and you say optimize an image that like represents this sentence, it'll do a really good job of that. I did not pull that up. But the way that they trained this network, they had 2 transformers. One was for text, one was for images. The text one looked at words, each got a vector, and there was like a list of word vectors. And the image network had images broken up into patches. So each patch got a vector, and then they relate to each other. It kind of knows where things are. It gets like a position encoding added into each vector. So it can tell like this is the top left patch of an image, this is the bottom right, and they're this far away from each other. So it's got that in the data, and it's only predicting, are these examples, image and text, paired, or are they not? If they're paired, then their embedding in the output of the 2 networks should be identical. And if they're not paired, then they should be maximally far apart. So they're using cosine similarity, which like isn't really important, but they're just training this thing to match up paired data. And it's got 500 million pairs, and it's seen some really good data from the internet. So it's learned like a bunch of stuff. If you show it an image of somebody, like some celebrity's face, it knows the name of that celebrity. It'll like pull out that word. If you type in like Keanu Reeves or whatever, it'll show you an image of Keanu Reeves' face. If you just like say optimize an image that matches this text embedding, it'll give you like the image embedding for that.
How big is the weight file?
330 megabytes. Yeah, it's crazy. This is like a small network. It's not the size of like GPT or anything.
How big is GPT?
It's like 185 billion parameters.
Okay, yeah, this is not that. This is not a billion parameters. It's less than that. It's like hundreds of millions, I guess, but
How many GPUs and days it would take?
well, definitely a lot. This is like expensive to train. They just gave us the pre-trained weight files. This is OpenAI that trained this, mostly because of the data set. They have like, so yeah, their data was really good. Like they got 500 million image pairs that are like well sampled from the internet. This thing knows like every meme you've ever heard of. You type in like the meme, it'll show you the meme image. Like it's got that remembered. It can remember some really good details. So we're looking at this, even though it's like small network, trained on great data, which gives us more interesting attractor structure.
Wait, quick question.
Yeah.
About Clip. You were talking about how you can like get it to generate an image.
Yeah.
If you give it the same sentence, does it always generate the same image?
No, well, so part of that is because of like you're starting at a random initialization of an image and you're optimizing. Yeah, so this isn't a generative model. You're just like kind of like going backwards through it. You're doing like a deep dream kind of. But instead of looking like deep dream, when you start at an image and you like get these weird artifacts in it that represent what you're trying to optimize towards, this will produce like natural looking images.
From random image.
Yeah, from a random starting point. Like you can have like a uniform like gray starting point.
Oh, not noise, just uniform?
Yeah, you can. You can just start at like zeros, whatever. And this is optimizing towards the text embedding, which is only trained to match the image embedding. So if you say, here's the embedding of this random image or uniform gray or black image, doesn't matter where it started. Just go towards this point in embedding space that is shared between the two networks. And so it'll go towards whatever the text embedding looks like, and that happens to be the matching image, or its understanding of what a matching image would be from this data set of paired data. Okay, so I'm looking at this the same way as the other networks. We're like mostly just taking like uniform grids. What I started doing is taking grids that are on a sphere, so just like points sampled equally far apart on a like sphere. They're all an equal distance from the origin, same radius. And that way we're looking at orientation, because that's like what most computation is being done with in these networks. Their distance is getting normalized. So if we're looking at a grid, we're kind of only seeing like 1D that gets projected out, and it's like on a flat line. So if we're like getting points on a sphere, then we're seeing a better projection of the attractor, basically. Like if we're looking at a 2D slice of the attractor, which is what we're doing here, we'll see like more of the attractor represented in those points. So we're on a sphere, but it'll like be plotted as an image still, so it's the same. And these attractors in CLIP are higher dimensional. They're like occupying more of the space. So some of those images I just pasted in here, we can kind of look at them. There's the visual transformer and the text transformer. So the visual layers, if we like take a 2D grid on a sphere and then iterate for 250 steps and see what that image looks like if we color code by the 2 norm, we'll get this pattern here. This might continue to change, but like things are kind of gonna, like they're gonna move together if they're nearby each other, and there's like sort of decision boundaries, right? So there's these like circular areas in this projection where these points are all kind of moving together, they're changing in color together, and then points on the other side of that circle are moving together.
Sorry, how are you projecting the sphere onto the 2D plane?
What I'm doing is I'm taking things on a sphere and projecting using principal components of the weights of that layer.
The first two principal components, so X and Y.
Yeah, so like I'll do points on a sphere, get their 3D coordinates, and then take the 3 principal components, but like really we're only in 2D. So they start at that point, they go in the function, they'll move. They're in 512D now, like they have a component in each of those 512 dimensions that they didn't before. And then what we're seeing here is projecting back down onto that sphere.
And then the sphere is wrapped out onto a plane, like with a Mercator projection?
Yeah. So just like we're seeing the sphere like flattened out, basically. That part's not super important. If I did this with a plane, we would see a different thing, a different slice of the same attractor. This is all the same process that we showed in the beginning, where we're like going in, normalizing, doing the residual connection, going back in. So it's the same points, we're just viewing it a different way. If I pick different principal component axes, which I can do, we'll see a different slice of the same thing. So in the first layers, like in this visual network, we see sort of like these blob kind of patches. And then later on in the network, the same kind of thing, like blob patches. And in the middle, like layers 6 and 7, there's maybe some more interesting regions. And then in the text network, which is what I'm showing here, things are, they definitely look different in the text network. Like the visual is like more smooth, and the text network has more like discrete regions and boundaries. The coolest layer,
I thought I saw like
this one.
square edges a few months ago.
Yeah.
Coolest layer.
Yeah, the coolest layer. Yeah, the coolest layer is layer 7 in the text one. So, yeah, this is the first, first layer in the text network, has these kind of like square edges. This is a flat view of a sphere, so that might be a different shape if it's like on the sphere. This just happens to be how these things get color-coded in their distance from the origin. this is like totally just a visualization. There's not much you can say about this, except, will these points go to different places? And points that are near each other and colored the same move together. And points that are a different color are like across some decision boundary of the network. They're in a different place in the space, they're colored a different way. In order to understand what this means, we'd have to actually like determine some property about the attractor, which we'll get to. So
So you basically downloaded their trained clip model and
Mhm.
then you're extracting each layer and trying to
Yeah.
process that.
the other point to just add here is there's no data involved. I'm not taking any images or text and feeding it in. I'm just picking a point in input space. So every piece of data is going to get some point. It'll end up at a place in the hidden embedding. Some of these points we're sampling might not be interesting at all. They're not where the data is. I've looked at that a bit, and like the places with interesting decision boundaries and like lots of different like regions in these visualizations are where the data is, because that's like how the network was trained. And then like large areas where not much happens, there's not data there. Is kind of what's going on. Yeah, but this just kind of like looks like it's just a visualization. This is showing us about these high dimensional attractors. We're just getting a 2D slice of it. But we can calculate things about those attractors as well.
I have a quick question. So, how sure are you that step 250 for clip is actually a good benchmark to reach the attractor?
Oh yeah, that was
score?
totally arbitrary.
Okay.
It's not. This keeps changing.
Okay.
So clip converges faster than most random networks do,
Okay.
and it converged faster than that face network did. That's in general what I'm seeing is like networks that are trained on good data have more interesting attractors. They also converge faster to them.
What do you mean, good data or more data?
More data, good data, either way, whatever. Just good data. It's a really general phrase. But if this was trained on 500 million images and text, and the other network was trained on a few face key points, and they're totally different. This is better data. And any measure you would use to say that, like if you tried to calculate stuff about the data, which people have done, you would get an indication like, well, this data has more structure to it. Like it is more complex. In the embedding, it lives in a high dimensional manifold. That stuff people have looked at, and like the data clip was trained on is going to be way better than the face network I used, basically. Okay, so we're going to kind of go on a different direction now. Sorry about that. It's just how these slides got thrown together. But the problem here is we have high dimensional attractors, and we can only see a 2D view of them. We probably want to like know more about them officially. Like we want to do stats on those attractors, or we want some kind of indication of, well, where are the interesting regions of input space? Like this network is like deterministic, right? Like it's a program, it's a weight file. Those weights are not changing. If you have 1 point in input space, it's going to go to 1 point in output space. Like we're on a vector field, right? Like there's one vector from every point to where it's going to go. And as we're iterating, we're just kind of like moving through that. We're following a vector, we're following another one, and so on. This is deterministic. It's not gonna like change at all. There's no randomness. So we should be able to say something about the different regions of space here. Like why is one region colored the same way, and then you cross a boundary, it's colored a different way? Well, we should probably be able to look at the weights and know something about them that would tell us about the regions of space here. And that would maybe let us not have to deal with 512 dimensions and not be able to see things that occupy many dimensions if we're only looking at a 2D view. So this is like a nice visualization tool, but we need a way to deal with many dimensions. So if we actually look at the weight values, they relate to this input space. Like we could actually plot a 0 where if you're on one side of input space, your activation is negative, and you go through a nonlinear function like a ReLU activation is going to zero that out. If you're on the other side of that decision boundary, you're going to have the identity function. That's what ReLU is, right? You zero things out that are negative. You have the identity function on the other side. You could plot that decision boundary in input space. and you could view all those decision boundaries as like lines where that 0 is, and see what that looks like, and it would tell you, okay, here's the different regions of input space, but those lines don't really like intersect each other. They're in 512 dimensions. One's pointing one way, one's pointing another. So we need a way to analyze those weights and how they relate to the input space. And I've just made a little bit of progress on that. So here what we're seeing is hidden activations. If we're looking at a two-layer network, we've got input and output space, but then we've got those hidden activations, right? So if we look at the input space, each has like a preferred direction in that input space. So if there's like 2,000 hidden activations here, they're all plotted. Some are going to point in different directions in terms of like where their high activation is going to be. And on the other side of that, they're going to be zeroed out. They're all sort of like pointing a certain way. And that's an indication of where their like orientation preferences in this space. What we're actually looking at here is, again, a low dimensional projection. So it's along principal component axes. And we see like most of these small patches, I don't know how much you can see, are pointing down in this projection, right? And then some are pointing in a different direction. They're pointing up or left. So if most are pointing down, that's maybe just an artifact of this projection, but they're all like pointing the same way. They're all doing the same thing. When we're looking in this subset of space, when we're looking towards these two principal component axes, if we pick different axes, a different projection, we'll see kind of the same thing. It'll look different though. Most of these hidden activations are going to be preferring the same direction, and then some will be pointing in different directions. So there's like diversity there. There's also kind of sparsity.
Is there any way to like potentially, maybe that's what you did in the next slide,
What?
organize those to see like how much of the direction is shared? Like if you could somehow like.
Yeah, like sort this. So I did that a little bit of a different way. I don't have it shown here. Yeah, I didn't look at like the distribution, although
You know what I'm
that
saying, though? 'Cause,
that's
like,
definitely
what if-
related to like if you just do PCA on these and you see like how much variance is explained by each
Yeah.
component, it's kind of showing the same thing. Yeah, so it's kind of evident here without even doing that. This is now output space instead of hidden activations. And this is really sparse. So most of these output dimensions, there's 512 of them in this network. Most of them are exactly the same. They're low activation. They have the same orientation preference. These look more interesting than the hidden activations, which just like point in one direction. That's all they prefer. The outputs are like composed out of those hidden ones, right? So they'll have more interesting patterns. They're nonlinear. What this is actually showing is like this first top left image is the first embedding dimension. So if you started at one point in 512D, where you're going to end up on that first dimension is determined by that map in the top left corner, the second dimension by the second map, and so on and so on. And this is all, again, just referring to these two principal components that we picked to view this in. So we see this like really sparse activation where there's only a few dimensions that are going to be changed a lot in this direction. So along principal components 1 and 2, sparse activation, and then along different principal components, different sparse activation. There's like less than 30 or so active dimensions here out of 512 that are like high magnitude activation, large change being made to this vector. So we see like a relationship between directions in input space and resulting changes in output space. And they're different not only for different regions of input space, but also for different directions that we're considering in the function. So we've got sort of like this conceptual, like here's how computations are implemented. Basically, like if we pick a direction, that's kind of like a like neuron conceptually, right? You're saying like things pointed in this direction are going to activate. They're going to like fire in this particular way. They're going to get moved. Their output is going to have a vector added to it that moves along this sparse subset of dimensions. And if your vector is pointing a different direction, then along some principal components, you're going to have activation that moves different direction. That like is a nice property, I guess. It's cool that it's sparse. We want to be able to say more about that. So looking at the overlap of these, I guess, is probably going to be important, and I want to do that. Like getting, okay, here's the different directions we can look at in the space. Here's the different sparse activations. Here's how they're related to each other. That might say more about what's actually happening in input space here, in any projection of it that we're looking at. If you're starting at a point, there's one vector that says, here's where you're going to go. How is that defined by these sparse activations? So that is not done yet. This is where I'm at with that. But it looks cool. It's a cool finding. I don't know. That's what I got. The other thing I've been looking at, which is very related, but a totally different like way of analyzing things, this is also looking at the weights, but it's sort of like reducing them. What we're doing is we're taking regular algebra, which is like we have multiplications and addition in the feed-forward layers, right? We like multiply and add. We do our like integrate and fire. We transform to a different algebra where multiplication is addition now, and addition is just a maximum or a minimum of the inputs. This is called tropical geometry. It's a field of math that like uses that different algebra. You're now on like a semi-ring in like abstract algebra. So like you're not able to study this the same way you would like a regular function. But what people have found about studying this like different algebra is you can reduce a high dimensional structure to have some simple properties that like you can actually say things about the high dimensional structure from those simple properties. So if you'll see on the right here, it might be kind of hard to view, but there's lines and then there's points where they intersect. And in tropical geometry, an example from Wikipedia is on the bottom here. You've got those points and lines, and then you've got these like faces in between the points that are like formed by the lines. The number of sides that a face has, or the number of lines that meet at a point, say something about that region of input space, or that point in input space where that point is located. That like will tell you about the function in like really useful ways. So I'm not going to get totally into that, but we can do that for neural networks. Since neural networks are like not any kind of function, but just multiply and add, and here we're just doing add and then take the maximum, really just what we're looking at is which input dimension is going to have the largest effect on a hidden activation. It's kind of all we're showing. But we get the same sort of thing. We get these points that are in the space, and then these faces that have like 4 sides, 5 sides, 7 sides, whatever. That region of input space then, we can look at in one of these projections, see where that region is. Points that are in that region have similar properties. Like they were treated the same way by these weights because they're in the same face. They're within certain decision boundaries. If they're on one side of this line, they all have the same maximum term influencing what their activation is going to be. And if you cross one of these lines, a different term is now the maximum term. So it's a bit more complicated than that. We don't actually just care about the maximum. We want to look at the minimum too. We want to see like each sort of like region of 512D space, which is a little bit tricky to get into. But we can take all these lines and points and like list them out and enumerate them, and all these faces and enumerate them, and say these are regions of input space, they have these properties, they interact with each other in these ways. We can take the field of tropical geometry and sort of like apply it to neural networks and actually like build a theory of, okay, well, there's different regions of input space that interact. So I'm working on that, very early stages of applying that. There's one other paper I saw that kind of like planted a flag on tropical geometry for neural networks. It's not really like I'm doing this by choice, I guess. Like there's no intuitive reason why you should be like using this kind of algebra to analyze the networks instead of some other kind. This just seems like a useful way to describe regions of input space, sort of like treat them as discrete, like this region all has the same property. And then because we have like definitive things we can say about this face has 3 sides, it has this property, what does that property mean when we're doing backpropagation? What does that property mean when points are being transformed onto an attractor?
Where's tropical geometry?
It's like a field of math. I haven't seen it applied to anything. The people that published that paper about neural networks and tropical geometry just like said, hey, this is like a thing. Like neural networks are functions. They obviously could be analyzed this way. And they were sort of saying like, well, the neural network already is like in tropical, like it's in that reduced algebra, like they call it like min plus or max plus, where you just have addition and the min or max function. They're saying like a ReLU activation is a line, those lines intersect at points. What I'm doing here is actually converting the like function with multiply and add into add and max. So that hasn't been done as far as I know. Like that paper was kind of like calling it tropical geometry, but they were talking about it in theory. And they were like doing some math to say, well, there's an upper bound on number of decision boundaries you can have, which is good to say, but like that's as far as they got with that. So I want to use it for a bit of a different purpose, like relating it to the properties these attractors have. The reason for that is, we're looking at high dimensional structures, but what we'll see, I guess a little bit later on, although I want to wrap up in 20 minutes or so, is different regions of the attractor have different properties. Like some are preserving features of their input, they're moving inputs together. Some are like cyclical, some are chaotic, even on the same attractor. So why are those different regions different? We know data gets projected to it, it ends up at different places, but what can we say about different regions of the attractor and how they relate to the computations being done on the input? So that's the active direction that we're heading in. As far as I've got so far, it's just like confirming, yeah, we can actually like produce these plots of tropical geometry. We can actually like, list out the points and intersections. Yeah.
I have a totally random question. What inspired you to like come up with these ideas like tropical geometry and Lorentz attractor? Like it's so far off than what generally happens in neural network. I mean, like how you just come up with this whole like thought line of research. That's like.
Well, I mean, this is definitely like arbitrary. There's not like a
I mean,
reason.
it's very like not talked
All
about
I
in the
can
community. Like
say to justify it is that like, okay, somebody else put a paper out about tropical geometry and neural networks are in the title together. So like somebody's thought of this, it's like probably worth looking at. But the motivation, I don't know if I'm explaining it well. We need a way to talk about 512D space. Like, I can't just go do like box counting dimension calculations, which I had on a later slide. But like with a Lorentz attractor, you're in 3D, you've got 3 equations, you have X, Y, and Z, and you've got some other hyperparameters. You can tune those parameters and get different attractors. And you can fill out a dense grid of boxes that fill that 3D volume. And you can start analyzing, okay, which of those boxes occupy the attractor, or like, which of those boxes does the attractor occupy? You can count what the ratio is of filled boxes versus unfilled boxes. And that ratio will change as you change the box size, and that tells you about how complicated the structure is, how many dimensions, how many numbers would you need to describe it as how many dimensions it occupies. If we want to do that for 512D, we can't. I can't fill a 512D space with small boxes and start counting them, because we would need 2 to the 512th power to even split the space into 2, and then we would need hundreds of those, like 100 to the 512th power. We can't do that. So we need a way to talk about these attractors we're just seeing in 2D here statistically, and And we need a way to break down those statistics into like regions of input space, because points is not specific enough, or not like general enough. And then whole stats on the entire input space is too general. We need some kind of in between there to be able to say, what is self-attention doing? Which I don't have visuals for included here, but these are fully connected layers. We have this self-attention operation that is like taking an input at multiple different points in this space and recombining them and then moving through this transformation together. It's using these attractors to do computation. And we need to be able to relate the different parts of the attractor in order to relate, like, what is the computation? What does it mean that something is in this part of the attractor, something else is in this part of the attractor, and they attend to each other in this particular way? They get transformed to a new location in the embedding space that maps to a part of the attractor. Like, what's the relation between those? Well, if they occupy, where is it? If they occupy different regions that we separate out with this way of analyzing the network, and those different regions have different properties, and statistically I found that things that have 7 faces add up a certain way, things that have 5 faces add up a certain way, and we can say something about the way that they interact with each other, or what self-attention does in terms of tropical geometry. That's a way of like applying a theory to what otherwise is a series of points that we have to like talk about in terms of like just visualizing them is not enough. And what I did later is stats on all the points, which also isn't really the end of this analysis. Like other people have done that. I was doing it. We get cool phenomena, and then we're like, what does it mean? So hopefully this is like a good, just a way to talk about different regions of input space is all we're really going for here. And it's based on the weight values. And those weight values are not changing. They're in the weight file. They're like a program. What are they doing is the whole point. So I see that this applies to that is why I was looking at it. This is a better view of the actual like tropical geometry surfaces we get in the network. So we'll see like there's these different boundaries. It's clear that they are like in high dimensional space, and we project them down to 2D here. They're like overlapping in weird ways. But also they form discrete regions that we can analyze. And these look exactly like what you'll pull up on the internet if you Google tropical geometry. Like they have faces that have the same sort of shape and properties that abstract math functions people study with tropical geometry do. So that's a good sign. Like this is probably good to analyze with that field of math.
Do you consider like, can you go back real quick?
Yeah.
Do you consider like the ones on the edges of face or only the ones in the middle?
The ones on the edges too, yeah.
Okay. Because
Um,
even though the boundary is just the plot, it's not necessarily a line.
Right. So what will happen here is like we're looking at which term has the like maximum effect on the hidden activations. So that term is going to change a lot near the origin because the weight values are different. We add the input and the weight because we multiply them in the feed forward. We add them here. And so if you have a negative weight, that'll shift where like the origin is in this modified algebra. And it'll shift it differently for different dimensions. So the maximum term is going to vary a lot near the origin within the magnitude of the weights. And then when you go beyond that, like toward infinity, like even just a little bit beyond that, you have regions that just go on to infinity. There's no other lines there. They just extend forever. So what's interesting is just these regions where the weight values are like different or within that magnitude. That's where most of the data is anyway. So this is like a way to tell us, okay, which parts of 512D space are interesting is kind of what like this gives us. Haven't done anything with it yet though. This is as far as I'm at. So you're getting a very rough draft presentation. I think you can tell that by now. Okay, I'm gonna run through this next stuff pretty quickly because I know, Stephen, you have a talk coming up with the journal club. Don't want to run into that. But what I've been doing, just other ways to like look at these attractors is instead of studying the full like high dimensional attractor, just looking at a low dimensional projection, kind of like a different attractor using a totally different technique, but that also has interesting properties. So what I'm doing is iterating once, but then projecting down to what we would be visualizing. If we're on like a 2D sphere, we'll project down to that, and we'll throw away most of the information about where we were in the space. We'll just go back onto the surface. And then we'll iterate again, project back down to that surface, and iterate again over and over. We're kind of doing a cobweb plot, which is what's shown on the right here, where you are on a function, you project down to a line, like reflect over the origin, basically, and then you go back into the function and project back down to the line, and then back to the function, and you see where you end up. And so this cobweb plot is used to see, like, is there one location you quickly attract to, like a stable point? Is there like a like chaotic pattern going on here? Are there many places you could possibly go to? That's what those plots are used for. Basically, that's what we're doing. That's how I started looking at this, which was like kind of a mess and didn't know what to call it. But if we do this instead of studying the actual attractor, we get some interesting things. And some of that might not mean anything. Like it might just be because we're taking a random function and pulling out a random piece of it. And if we iterate a simple random function, we'll get some interesting stuff pretty often. So here what I'm doing is I'm on 1D. So I'm just looking at one angle around two axes. So picking principal component axis 1, axis 2, what angle are you around those? And iterating, projecting back down, what's the angle with respect to those axes? And if we do that for different axes, we get lots of different interesting patterns. They will look like this. So some of them converge to two fixed points, is what's on the left here, point and point. We see this alternating as we step out in time steps toward the edge of the circle. They're alternating because this is a discrete approximation of a function. And so if we go to one, we project back down, we'll end up at the other. But we're still on those two fixed points. And then over here, we have like a big chaotic mess. There's certain regions that will continue swapping between 4 fixed points forever or 2 fixed points forever. But eventually, they're going to fall onto some like chaotic mess that will stay chaotic forever. This is interesting. It has certain properties that relate to the full attractor. And the way that they relate is totally based on this stuff over here, the sparse activations in certain directions. So if you look at what would the attractor be in this kind of cobweb plot thing in these directions, it relates to which sparse directions are activating when you iterate. And I'm working out how those relate. It's kind of like as obvious as you would think, which is cool. That's cool, but it's in the works. Otherwise, yeah, we just get some like really diverse and interesting plots here, which is cool. One thing that I saw that I was very hyped up about, and I know I showed it to you, Elon, I don't know if I showed it to you, Will. This is just an example of 2 different axes in the train network in one of the visual layers of CLIP. And we see like a phase plot on the right here. What's actually happening in here, it's not well visualized, but I'll just explain it, is we have 2 fixed points, and then there's like this asymptote here. So there's a stable fixed point and an unstable fixed point. Points will get attracted to this region here, where we see lots of different dots in the scatter plot. Those points are going to go from the x-axis to the y-axis and then project back and go again. They're going to continue cycling around, falling into this asymptote, and then cycling back over here really quickly, and they'll end up somewhere else in this region. Different parts of this region of points here map differently to either the unstable fixed point or the stable fixed point. And it's really chaotic what that map looks like. I don't have it shown here, but I did do a plot for it. So eventually these points end up at the fixed point, and they don't leave that. They're stable there forever. but some of them continue cycling around over and over again because they go towards this unstable fixed point, they pass it, and they end up falling into the asymptote, coming back around to this region. I hope that's making sense. Do I need to explain that better? No? Okay, cool. So the time it takes for them to cycle around again depends on where exactly they go in this region. Sometimes they'll move really slowly, like they're doing an iteration, they're very small magnitude. And it'll take them like 100 iterations to cycle around again, or 300 iterations to cycle around again. Sometimes it'll happen really quickly, just a few dozen iterations. And then eventually, kind of unpredictably, chaotically, they're going to stop moving around this loop. So an example of that for one particular point is shown here. There's like this sort of like spiking that happens, moving around the loop, waiting a certain amount of time before moving around the loop again, and then eventually never moving around again and ending up at the stable fixed point. So we have like simple mathematical structures here, like fixed point, unstable fixed point, and this asymptote in this simple attractor that we made by like doing a cobweb plot on the full attractor. And we're getting this like random chaotic spiking pattern. We spike here, we wait a certain amount of time, we spike again. There's ones of these that like look like neuron firing from like a biological neuron, which is like kind of cool. It's probably like, I wouldn't say it's more than a coincidence, but like it is what it is. Like this is a computation implementing that like random chaotic spiking and then eventually terminating at an unpredictable amount of time, depending on where exactly it ends up in this linear region here. So that's really cool that this is in the network. If we just pick out two directions, we see this. We pick two different directions, we see something totally different. So cool, interesting. I don't know what to make of that. Yeah, hopefully we figure something out about that. I don't know.
So the x-axis there is angle?
The x-axis here is the angle around two axes that we just picked. And the y-axis is also an angle, but it's the next time step. So this is just like if something's at a point, where's it going to go next? And these points are like after many iteration steps. So this starts off kind of a mess and it ends up doing this forever. If we were to look at like an image plot of that same exact thing, what we'd see is like certain regions here end up at that fixed point very quickly and they don't change. But other regions look like this on the right, where we see kind of like a chaotic, like there's like period doubling going on in some of them, so there's like bifurcation happening. That's what we see in this particular plot. And again, in discrete time steps of that, but you could plot a continuous function here where there's like bifurcation along a curve. So we're getting those patterns. They're just kind of like implemented discretely. And they're just different for different directions. So it's like totally arbitrary that I just picked those two axes. They were the first and second principal components. And the angle around them happens to do this if you make a comma plot of it.
An asymptote around -3 radians.
Did I say that wrong?
-3 is around pi.
Yeah, so it's like right before, well, it's where the points kind of like fall off this linear region here, where they're not moving very much. Their input is very close to where their output is. There's like a very small change from the line, where this function that's approximated by these points intersects this identity line is where fixed points are. Like points are not going to leave this line once they reach it, unless they like cross it at an unstable fixed point where nothing is ever going to actually reach that point because it's not attracted to it. So all these points here are like slightly off this line. They're going to move a little bit away from where they actually started because the x-axis is where they start, y-axis is where they go. They're moving slightly negative because they start at this point, they're going below the identity line. They're going to move a little bit to the left in the next iteration. So they're moving slowly to the left here, down these points until they like quickly start moving away when you reach this asymptote. They're further away from the line there, they're moving further left, higher magnitude, and then very quickly, they move over here to the other side of the plot. They've crossed from negative pi to positive pi. And then very quickly, they're gonna like drop down here and then fall in this region again. So that's what we're seeing with that. I'm gonna skip past some of that. I did it in 2D too. We get cool things from there. I was making some cool fractals with that. That was kind of interesting. Like fractals like you would typically think about that look like fractals. They have interesting structure. Just by like projecting down to a 2D sphere or like a three sphere in 4 dimensions and like taking the angles there. It looks really cool. But that's just for fun. The interesting stuff is actually studying like the stats of these attractors. So what we can do to deal with these things moving around is using this wonderful theorem that gives us a way to have an alternate embedding based on the time steps. So what we can do, shown for the Lorentz attractor here in 3 dimensions, we iterate, we get like a time series. We can just take that time series. As long as we have enough time steps, it's actually twice as many as the dimension of the attractor is what we need, then we can just take a transformation of that time series, treat that as an alternate embedding. And what happens in practice for us when we do that is that time series is not that complicated. There's like a few different frequencies of sine waves you would have to add together to get that time series. So that's cool, we can study that. It's an equivalent attractor, and this theorem proves that the attractor actually has all the same properties, it has the same dimension and everything. So that's what I was doing. This is like we saw the face attractor, right? This is the same thing for clip layers now. So it looks like similar, it's plotted a similar way. It looks kind of like a mess. It's cool, visualized the same way. If I'm looking at the time series instead of the actual embedding, that doesn't move then. Like we saw that attractor kept looping around in the face network. This is a way to get an equivalent attractor that will not continue moving. We have like a cutoff where even if we kept iterating, the points would change. We can just say we did 1,000 time steps. We have a 500D embedding space. That's definitely enough to capture whatever structure's here. We'll take that 1,000 time step series, run it through an FFT because it's an invertible function, and get just a few numbers that describe this attractor. So what this is getting at is a way to describe how many dimensions the attractor actually occupies. Here, if I started with a 2D grid or 2D points on a sphere, and I iterate them in a time series, turn that into the embedding instead of the actual embedding dimension, and then do PCA on that, 2 principal components will explain almost all the variance. So if we have a 2D grid, we have a 2D slice of the attractor, this is a way to turn that back into 2 numbers, to say this is really only a 2-dimensional structure. It's a 2-dimensional slice of whatever we're looking at. So actually doing stats on the attractors is like where we're headed with this, what I've started doing. There's lots of ways to calculate like fractal dimensionality or like decimal number of dimensions you would need to describe a position on this attractor. Do you need 3 numbers because it's on 3 axes? Do you need 12 numbers, 100 numbers? We know we're in 512D or whatever space. We need fewer numbers than that to actually say what's the structure of the attractor. I'm going to skip past this, it's not important. This as well. Some other people have looked at calculating dimensionality of data sets in hidden embeddings. They're not iterating and looking at the attractors, which is like related. It's kind of the same thing anyway. A paper at NeurIPS 2019 published a custom measure of dimensionality that they said would work well for embeddings. They're looking at like if you have a point in a data set, what's the nearest neighbor? How far away is that point? How far away is the next nearest neighbor? And what's the ratio between those two? Because if you occupy more dimensions, there's more ways for the points to be close to each other. So the distribution of distances is going to be different And the slope at that tail end of the closest distances is going to tell you what the dimensionality of the attractor is, or in this case, the data set in the hidden embedding. So they published this paper. They found something that this other lab also found, which is that the dimensionality of layers through a network has certain properties to it. It'll blow up at first, get high dimensional, like dozens of dimensions or even hundreds, but not the full embedding space. And then by the last layer, it collapses down to a low dimensional structure that is linearly separable for a classifier. So that's a cool phenomenon that they found. It like holds true in not just neural networks, but actually also in data from the visual cortex, which is cool. I've been able to see the same thing when I do the calculations. And when I use different measures of dimension, I see the same thing too. So what I've been looking at is doing correlation dimension, which works well for points, because box counting is kind of a hassle in 512D. If you just look at points and you get their distances between them, and you look at the closest distances and what the slope of that distribution is at that tail end of the closest distances, that will tell you, if you do this calculation, what the dimensionality of the attractor is, which just means how many numbers do you need to explain all the variance of the points. That dimensionality, if I do a 2D grid like we were visualizing, isn't that, like, it's two-dimensional basically is what we're seeing, because we have a 2D grid, a 2D slice of an attractor, still 2 dimensions. You only need 2 numbers to describe where a point is. If we just do like a random normal distribution of points, then we see the actual dimension of the attractor, which for a 512D embedding for this particular layer was like 80, 90, 100. And then later on in the distribution, you have a lower dimension calculation, which I think actually says something about the structure of the attractor too, which like the theory is not known on that, but I want to do stats on it. And conveniently, we can do stats on it because I got my hands on a data set of 50,000 trained networks that a Google Brain team trained. They were doing a grid search for like a problem that they had.
All the same task?
Yeah, all trained on ImageNet for the same task, 2 different versions of ImageNet. Yeah, 50,000 networks, like a grid search. So some of them suck, some of them were like bad hyperparameters, some of them are really good, some of them are more layers, some are less, all different like properties of the grid search. So by doing these correlation dimension calculations, intrinsic dimension calculations, and doing stats on all of those networks, that might like show us some new phenomena, like what these labs have seen. But then also, instead of just doing one calculation for this whole space, we do want to know about individual regions of the space. And so looking at the Lyapunov exponents for a particular point, which just kind of tells you like, if you have 2 points close by each other, how do they deviate from each other? If you got a point and then a point slightly to the right of it along a particular axis, how far do those points end up from each other on the attractor? And what's like the ratio of that distance over time? That's what the Lyapunov exponent will tell you. And then you can turn those into a dimension calculation as well. That can be done for individual points. You can also sort of average it over regions of space. So if I'm doing that, then we can like kind of combine that with the tropical geometry stuff and get statistical calculations for different regions of input space, do stats on multiple networks, and sort of break down, okay, here's how regions of input space relate to each other, and then eventually get to self-attention. That is, I guess, a good strategy, I hope, for coming up with like a theory of, like in these terms, how is computation being done in the transformer? That's my plan. Since I have like 2 minutes left before you gotta go, I'll just show the face network. The answer to what we found out about that is the network sucks. I trained it to predict distances, but I also showed it distances in the input. So it learned to ignore but preserve the distance. What's happening on this loop? Everything is being mapped to where it was in the input sequence. It's looking at like a video of faces, and it sees the distances. It has to predict the distances. All it's doing is preserving where something was in input space, so that when it comes to prediction time, it knows Well, if something was at this time step, and the point before it has this distance of key points, and the point after it has this distance, I should just interpolate between those two. That's what this loop is doing. It's taking missing time steps, using their location to interpolate. They should go between these other 2 points here on this loop because its time step was in between the other two. So it's doing interpolation from position and just preserving, but not learning anything meaningful about phase structure. So we tried to predict stuff about phase structure with this network, and it sucked. It wasn't that good. We could get accuracy, but it wasn't like, there was no benefit from pre-training, is what we saw. That was because we didn't train this thing to learn anything about long-range dependencies between like one input and another input a second away from each other. It didn't have to know anything about the phases. So by looking at this attractor and plotting pieces of data onto it, like seeing where it ends up, we figured that out. That was like kind of cool and useful. So that's nice. The other thing that we saw is in this embedding in the last layer, right before we predict distances. The embedding is low dimensional, but it's like more than 3, right? It has that property that the other labs have found out where like dimension in early layers blows up and then it falls down by the last layer. And in that last layer, even though it's like however many dimensions, distance is predictable, like the variance in distance is explained by one principal component, which is kind of really cool that even though it's like nonlinear structure, you only need a linear transformation to separate out phase distance in that embedding. And in these transformers that are like pre-trained and fine-tuned on many different tasks, that's what's going on there. Like you only need a linear sometimes or like very simple transformation to pull out really interesting properties for many different downstream tasks from this one embedding because the embedding is well organized. So that's cool, I guess. And I've been doing plotting in 3D too, just to like get an idea of what these structures look like. So it might be hard to see because this like requires OpenGL rendering, but oh, that is lagging. Well, anyway, I'm plotting the points in 3D using a different projection and like able to like fly around them with like Microsoft Flight Simulator type controls. So that's cool and fun, I guess. Not really like scientific, but yeah, that's like fun to look at. And I'll probably have that up in the library later when I get a controller set up for that. So that'll be fun. And the other thing that we can do with this here is like box counting dimension calculations, because we can't do that calculation in 512D, but if we project down to 3D here, we can do our box counting. This is like really interesting chaotic structure. There's some regions that are like preserved structures. There's some regions that move around really chaotically. We could do stats on that. So that's where I'm at. Thanks for listening. Sorry for the mess. Yeah, that's it. 158. Good to go, Stephen.